Hello class, and welcome back to Control Systems lectures. In my last class I explained to you the course and the things you expect to do. It was more of an introduction to control systems. And so in this lecture we will now proceed to go to further things. First, having the background mathematics that we need for this subject. So we'll be looking at modeling in the frequency domain. At the end of this lecture, you should be able to find the Laplace transform and inverse Laplace transform of differential equations of dynamic systems. I believe that this is not the first time you'll be doing Laplace transform. You already did it in mathematics. And what we are doing in this class is just a revision, a quick revision of this mathematical background that you need for control systems. You should be able to develop the transfer functions of linear time-invariant systems for electrical networks. For mechanical systems, this will be translational systems and rotational systems. And then electromechanical systems like motors. Motors, for example, is a good example of electromechanical systems. And then we will also do linearized nonlinear systems. You should be able to linearize nonlinear systems. So we start with differential equations, and we're going to review the differential equations and Laplace transform. There are different types of differential equations. We have differential equations. It's an involving it involves an unknown function and one or more of its derivatives. So we have the ordinary differential equations, ODEs, where the unknown function is a function of only one independent variable. And then we have partial differential equations, where the unknown function is a function of more than one independent variable. The derivative of the highest order with respect to the unknown variable determines the order of the differential equation. If for a differential equation, for example, this differential equation an x to the power n plus an minus 1 x to the power n minus 1 plus continues up until a1 x dot plus a0 x equals to f of t. Note that these powers are the derivatives. So it's dot means this is a derivative. This stands for dx dt, where x is a function of time, and x to the power n, as I've just explained, is dnx over dt, which means this is the number of differential equation. If n is 2, then this will be d2x over dt2. So if for a differential equation like this one that we've given, which is a function of time, all coefficients, these coefficients a1, a0, a1 up to an, are either constants or functions of the independent variable t, then the ordinary differential equation is linear. Otherwise, the ordinary differential equation is nonlinear. So what are we saying? So this is a differential equation, and if all these constants, these coefficients, are either constants or functions of the independent variable t, then ODE is linear. If they are not constant or if they are not functions of the independent variable t, because this is a function of t, then that will introduce another derivative, and so the equation becomes a nonlinear. The ordinary differential equation becomes nonlinear. So if f of t is 0, then the ordinary differential equation is called homogeneous. Otherwise, it is non-homogeneous. Now let's look at Laplace transform review. The Laplace transform method allows us to represent our models in the block diagram form, as you can see here. So it makes it easy to analyze. And if you have an input here, r of t, then you have subsystems, and then you have an output here, which is your c of t. Note that the input R of t stands for reference input, and then the output C of t, the C of t stands for controlled variable. With time, we'll define these terms, and you will be using them very frequently, so you will get to understand them. But just know that R of t is referred to as reference input, and C of t is referred to as controlled variable. So what are the advantages of the Laplace transform? Rather than trying to solve an ordinary differential equation with initial conditions in the time domain, where we look at derivatives and possibly integrals, we transform the data to the S domain, in which the transform problem becomes purely an algebraic one. So this is one of the advantages of Laplace transform, that we transform an ordinary differential equation to one that can be solved as an algebraic equation. The solution is ultimately transformed back to the time domain. So first we transform from the time domain to the S domain to make the analysis simple. And then after we've done the analysis, the solution is then ultimately transformed back to the time domain in order to find the solution of the original problem. In the Laplace transform method, both the transient component and steady state component of the solution can be obtained simultaneously. If you remember in differential equations, when you were solving them, you have the particular solution and you have the general solution. And you separated these two and solve for the two and then combine them. Laplace transform is able to provide one solution that gives you both the transient component and the steady state component. So now we review some of the key functions of the Laplace properties of the Laplace transform. Before then, the Laplace transform converts a function x of t of the real variable t, that is t stands for time, into a function of a complex variable denoted by s. So s stands for complex variable. If f of t is defined for all time or all t greater than or equals to 0, then the Laplace transform of the function in time is equals to f of s in the Laplace transformed in the s variable, and this is converted by taking the integral from -0 to infinity of the time function multiplied by e raised to minus st dt. So this is the equation that we use to convert from the time domain to the Laplace transform, where of course s, which is the complex variable, is sigma minus j omega, and we know that this is a complex number with the real part and the imaginary part, and this is your s, which is the complex variable. It is common practice to denote a time-dependent function by a lowercase letter such as x of t, so x is a lowercase, and then its Laplace transform by the same letter but in capital, so you see x of s. And that's why even in this equation, when we are expressing the function with respect to time, we use the small letter f. When we express the function in terms of the complex variable s, we represented it by using the capital F. However, note that your s is still in lowercase and it must remain in lowercase. Transforming the data back to the time domain is done through what we call inverse Laplace transform, and given by this equation. So the inverse Laplace transform of f of s, so this is now in the complex variable domain, and we're taking it back to the time domain by doing an inverse Laplace transform, and the equation is given by 1 over 2 pi j with the limit of the integral where the real component minus j omega infinity to sigma plus j infinity, and then you put in the function in the complex variable multiplied by e the exponent e raised to st ds, and this will give you f of t u of t, where u of t is the outcome of this analysis, and ut is 1 when t is greater than 0, and u of t is 0 when t is less than 0. So important Laplace transform pairs. There are some very important Laplace transform pairs that you need to know, which are very essential for control systems. We have the step function, we have the impulse function, the ramp function, exponential decay function, the sine and cosine waves, we know all these. We have the damp oscillation, and we will go into details on these different pairs. So if you take the unit step function, for example, if u of t is equals to 1, the unit step function u of t is equals to 1 if t is greater than 0, and the unit function is equals to 0 if t is less than 0, and it is undefined if t is equals to 0. So this is the unit step function, and if you have u of t, which means you have a function in the time domain, and you want to convert this now to the Laplace transform, so you take the Laplace transform of the time component. This will be given by multiplying your time function with an integral 0 to infinity e raised to minus st ut dt, where this is your time function. So if you take the integral of this, if ut, say ut is 1, because we said it is a unit step function, so ut will be 1, then we have this will be equals to the integral of e raised to the power minus st dt. And if you take the integral of this, it gives you e raised to the power minus st over minus s. If you put in the limit from t equals to, as t tends to infinity, to t equals to 0, we will have u of t is equals to 1 over s, because if you put in t equals to infinity, this vanishes, and then if you put in t equals to 0, you will have 1 over s. Just put in the limits and you arrive at u of s is equals to 1 over s. Now this is the step function where you have a magnitude a. In this case, we didn't have a magnitude, it's a unit vector, a unit step function. But if you have, let's say, a, which is a constant, multiplied by the unit unit step, then you will have the a, and if you put in this into this equation and you differentiate it the way we've done here, you arrive at a over s. So you see, if it's a unit step, it's 1 over s. If it's multiplied by a magnitude a, is a over s. So if you have, for example, 5 ut, this will be 5 over s. So now we have an exponential function. In this exponential function, this is the function in the time domain. If you take the Laplace transform of this function, you have to multiply it by this integral with e exponential to power minus st, and this is your time function. You take the integral, and you can see that this will transform to e raised to power. You add the two powers, which is s plus a t, and then if you do the integral of this, you have the exponential to the power s minus s plus a t divided by minus s plus a. If you put in the limits, you will arrive at 1 over s plus a. So if you have an exponential function, this is what you get as the Laplace transformed. So if a is 5, this will be 1 over s plus 5. If a is 3, this will be 1 over s plus 3. Then for the unit ramp function, it's given as t. So that is for the unit ramp. And unit ramp is t if t is greater than 0 or greater than or equals to 0, and the ramp function will be 0 if t is less than 0. So if you do the Laplace transform, since the unit ramp is just a t, you have 0 to infinity e raised to power minus st t dt. The integration by parts, if you do integration by parts, you will then get your Laplace transform of the ramp function to be 1 over s squared. So you can go through this integration by part and then arrive at 1 over s squared. All right. So here we have some Laplace transform pairs and the tables where you have the transform equation, using the Laplace transform equation, we can develop these tables. For example, this is a function in the time domain, and this is the Laplace transform. All you need to do, if you come here, is for every function, you integrate it between 0 and infinity, and you multiply that function with your e raised to power st, and this will give you this that we have here. You can see this is your unit step, which is 1 over s squared, and this is t, which is your ramp function, 1 over s squared. And then if you have a power to the ramp, then you have n factorial over s to the power n plus 1, and it goes on. And these are the sine and the cosine. You have for sine, which is omega t, ut will give you omega over s squared plus omega squared, and for the cos is s over s squared plus omega squared. So usually this table is provided for you when you are solving a problem, but not when I'm testing you on Laplace transform. But if you're solving other problems that you require these pairs, I will provide the table to you. Let's look at a few properties of Laplace transform. Laplace transform has big advantages for control systems, and you have the following properties: the linearity, the differentiation and integration, frequency shifting property, and then final and initial value theorems. Then we have the region of convergence, and you'll see very soon as we progress in this class the importance of these properties in control system. So let's look at the linearity property. The linearity property says that if you take the Laplace transform of a multiplied by a function, it will give you a multiplied by the Laplace transform function. That's what it means. So here you perform your Laplace transform and you arrive at a f of s. So nothing happened to the a, so it's a linearity. So multiplying a function of time by a constant multiplies its Laplace transform by the same constant. And the linearity property also obeys superposition, which means if you have two functions and you need to take the Laplace transform of f of t plus g of t, the Laplace transform will be f of s plus g of s. So combining these with the previous results, we can say that if you have the Laplace transform of a f of t plus b g of t, it gives you a f of s plus b g of s. So these are the Laplace transform of the time function, and your constants are just retained. So this is part of the linearity property of Laplace transform. Then we have the frequency shifting property, which is multiplication by an exponential. If you take the Laplace transform of a function multiplied by an exponential, so you have a function f of t and an exponential. So this will give you the Laplace transform. You know, this is coming from the Laplace transform, and this is your function here. If you do the Laplace transformation, take the integral and put in the limit, you will get your Laplace transform of these to be f equals to s plus a. So you can see that if the function, the power of the function is at, you have s plus a, which means if you have e to the power of 5t, it will give you s plus 5. If this is positive, then this will be negative. So multiplying the function f of t by e minus at is equivalent to replacing the variable s by the quantity a plus s, or s plus a, wherever it occurs in f of s. Then you have also the differentiation property. Take a first derivative, for example, f of dot means df dt. So this is a function of time, but its first derivative. You Laplace transform it, you take the derivative multiplied by the Laplace transform equation, and then you do integration by parts. You take u is equals to e raised to minus st and dv equals to dft dt. Once you do this integration by part, you will then arrive at the final solution that the Laplace transform f of t dot is equals to s f of s minus f of 0. When f of t is discontinuous at t equals to 0, we consider f of 0 equals to f0 minus, which is equivalent to saying that any discontinuity at the time origin is considered to occur just after t equals to 0. Just after t equals to 0. If you have the second order, that is Laplace transform here of double dot, then you can see that in this case you have s square f of s minus s f of 0 minus f dot of 0. So there is a sequence that is being performed, or that is being occurring here with the derivatives. So we can write a generalized form, and which can become your generalized equation for solving for differential equations. So if you have the Laplace transform of a d to the power n f of t dt n, this will give you s to the power n, which is s to the power n. In this case, n is 2, so s square f of s minus s n minus 1. So if n is 2, this will be n minus 1, which is 1. That's why we have s here. And then we have f of 0, and it goes on like that. And so if you use this equation, you then be able to find the Laplace transform for any derivative to any power. Yeah, for the integral, it's this complicated equation here that you apply Laplace transform of f del lambda, f of lambda d lambda. This will give you 0 to infinity, 0 to t. Now you are Laplace transforming this to the Laplace transform, because this is the integration. Then you have e raised to the power st dt. So again, you apply this derivative or integral with your Laplace transform equation. You integrate by part, and then you will arrive at the Laplace transform of an integral is 1 over s f of s. Remember, the Laplace transform of a differential is s f over s. So since integral is the inverse of differentiation, you can see that if you take the Laplace transform of an integral, it will be 1 over s. Well, this Laplace transform, I believe, is something that you've done in mathematics, and you can go through your textbook. You can see page 37 where I got this theorem, and then go through the Laplace transform theorems and their properties. So these are the various theorems, and the one I need to point out here is the final value theorem, which states that f of infinity is equals to limit at s tends to 0 s f of s. And the initial value theorem states that, so this is the time function at 0 is equals to the limit as s tends to infinity s f of s. We will come across this again as we go on in this course. So the initial value theorem states if f of s is a rational function and the degree of the numerator polynomial is less than that of the denominator, the limit of f of t as time approaches 0 through positive values denoted by f of t is given by this equation. So this is the equation: f of 0 plus is equals to limit at s tend to infinity s f of s. So time domain, complex domain, or frequency domain. And then the final value theorem, which is very, very important theorem you need to take note of. It gives us very important information which you will see in the future. It says that if f of s has no poles in the right half of the complex plane, and with the possible exception of a single pole at the origin, has no poles on the imaginary axis, the final value theorem states that so the time function at infinity will be equals to the result of your Laplace transform at s equals to 0. So you see, if you have a time function and you want to find out the behavior of this function at infinity, all you need to do is to get the Laplace transform of the system and then substitute s equals to 0, and that will give you the result, where f of infinity denotes the limit of f of t as t approaches infinity. So you can say that the system have arrived is steady state condition. So what is the general procedure of application of Laplace transform? First, you write and immediately transform the differential or integral differential equations describing the system for t greater than 0, evaluating all the initial condition terms and terms that appear in the transform equations. Secondly, you solve these algebraic equations for the transform of the output. Then evaluate the inverse transform to obtain the output as a function of time. So this is the procedure, and this ends our review of Laplace transform. And the next thing we're going to be doing is to review the differential equations, which is something you've also done, how we solve differential equations the way you did it in mathematics. Thank you very much for listening.